Okay, so today I'm going to go through how you would set up and then run a two-way between factor ANOVA in SPSS. So unlike the one-way ANOVA where you have one independent variable measured across a dependent variable, you have two independent variables with a two-way ANOVA measured across your dependent variable. So for this example, I'm just going to go through the two-way between factor ANOVA, and that's where both of your factors, your independent variables, are essentially measuring between different conditions or between different genders. So for this example, which I've laid out here, we've got a treatment condition. So for this one, I've just made up some data. We're going to examine the effect of a placebo, which is like a dummy, and then a low caffeine dose, doesn't matter what dose it is, and then a high caffeine dose, and then the exact same for men and as for women. So we have treatment as a factor, and that has three different treatments, so that has three levels, and then gender, we've got male, female, so there we have two levels within that factor. And then our dependent variable, what we're measuring, is essentially heart rate. Okay, so if we were to set this up in SPSS, which is not entirely straightforward, but I'll go through it now. So we need to set up our factors. So in SPSS, if we're setting up a between factor, we have to list it as a nominal variable. So here we can call one condition or treatment, it doesn't really matter. And we have to label this as a nominal variable, otherwise SPSS will set it automatically as a scale variable. And then we need to label what our levels are within that factor. So if we say number 1 equals placebo, number 2 equals low dose caffeine, and then number 3 equals high dose caffeine, then that's the first between factor done. And then we have gender. And we enable this a nominal variable. And then same, number 1 we'll call that male, number 2 we'll call that female. Okay, so there are between factors or our nominal variables, but now we need to list a scale variable, so that's our dependent variable, basically what we're measuring, which is heart rate. Nope. Can't have a space. Okay, and then that's a scale variable, so we don't have to label anything here because that's just going to be our heart rate values. So if we go back, we can see this now. We have the nominal variables as these three circles, and then this ruler for the scale variable. So you can just type 1 here, and you can see it comes up as placebo. You can click this button here to switch it. So if I just say 1, 1, 1, because we've got 3 data points for each level, 2, 2, 2, 3, 3, 3. And then we want men first, 2, 3. And then we basically want to do the exact same for women. So now we've got all the different combinations across our two factors. So now we just need to copy and paste in whatever that heart rate data was. So just here, you can copy and paste from Excel into SPSS and vice versa, which is useful. All right, so now what it's going to do is tell us, is there an independent effect of condition on heart rate? Is there an independent effect of gender on heart rate? And then is there an interaction between condition and gender on heart rate? You don't get interactions with a one-way ANOVA, so this is the first time you'll see it. The two-way ANOVAs, the three-way ANOVAs, they measure all these different interactions. So we'll get 3 main p-values, but before we get there, we should check some of the assumptions. So we need to check for normality, so we can use the Shapiro-Wilk test. This is the same as a one-way ANOVA, and even with t-tests. So for that, we can go Analyze, Descriptive Statistics, Explore. So here we can put our 2 between factors in our factor list box, heart rate in our dependent list box, and then all I do is click. Actually, that's right, I've already done this. So I just have normality plots with tests, so that gives us what we want. And we're looking here for a box here, it is test of normality. So we're looking for the Shapiro-Wilk box because this is for low sample sizes, and for higher than 0.05. If it's lower than 0.05, that assumption has been violated. So here we've got heart rate, placebo, low dose, high dose. They've all been met. And then for gender, here male and female, higher than 0.05. So the data is normally distributed, so you've got that assumption that's met. There is another assumption, but you have to get that output when you actually run the two-way ANOVA, which we'll do now. So for this one, if I just go back, we have to go to Analyze, General Linear Model, and Univariate. So here we have one space in our dependent variable box, which is what we want. So heart rate goes in there. And then we have multiple spaces within our fixed factors box, which is where our between factors go. So these are our nominal variables in this example. They go in there. And then we can select what we want. So for plots, this is just my preference. So this is not essential. You don't actually need this. It's just for visualization purposes. Fine. Then postdoc. So this is where we start to determine where the differences are. So I've got Tukey selected because I've already run this just to check. And then estimated marginal means. This is our main postdoc test. So here, select everything, put it across, and then I normally select Bonferroni here. So now we're not just going to get the p-values to say there's a difference. We're going to be able to see where those differences are as well. And then options as well. So homogeneity of variance test. This is the second assumption typically you'd need with a two-way between factor ANOVA. That's to check if the variance is equal across your factors in relation to your dependent variable. And then I've got some descriptives as well, like mean and standard deviation, etc. So once we've got all that selected, we can now run the test. So always check your warnings. This says post-hoc tests are not performed for gender because there are fewer than 3 groups. Okay, because we're only comparing men and women, there's only one comparison to make. If there was 3 groups there or 4 groups, there would be multiple comparisons. So here, because it's 2 groups, A versus B, let's say, you can only compare that one way. So you don't need the post-hoc test because the initial comparison gives you the p-value you're looking for. Okay, so now you've got between subject factors, it gives everything labeled for you, but we can just move down. So this is the first box, Levine's test of equality of variances. So this is that assumption, not just normality, but the variance check. So for heart rate, you want this top row based on mean, and it's higher than 0.05. So this, again, like normality is what you're looking for. You're looking for higher than that 0.05 mark. So it tells us that that assumption has been met, which is great. Because this two-way ANOVA has no repeated factor, it's all between factor, everything you need is in this box here, tests of between subject effects. So for condition, so this is placebo, low dose, high dose. If you go across, it tells us that there is a main effect of condition. So it's saying that there is an effect of caffeine dose on the dependent variable. This just doesn't tell you where it is. That's what the post-hoc tests are for. And then it says for gender, when you compare men versus women, there is also a difference. But interestingly, condition times gender, this is our interaction p-value, arguably the most important p-value, saying that there isn't a significant interaction, meaning that condition and gender have effects on their own on heart rate, but they don't interact with one another to influence heart rate. So this is quite an easy output, really. If this was an interaction, then it would be a bit more difficult to explain. So maybe in another video I'll do that. But basically, there's an effect of condition. So when you go from placebo to low dose to high dose, or you go from male to female, there are those independent differences, but they're not interacting with one another. Okay, so there are differences. Where do we find them? So let's go to condition. So here we've got some descriptives. So mean, standard error, you can just look at the mean really, 58, 67, 76. So it goes up with the caffeine dose. And then you get your pairwise comparison. So this is comparing the different conditions against each other. Placebo versus low dose, significant at the adjusted Bonferroni level. Placebo versus high dose, different. In fact, if you look down this column, they're all different. So that's interesting, but it doesn't tell you if that's men or women. It just says placebo is different from the other doses. In fact, they're all different from each other, but it doesn't give you any effect of gender. Likewise, if you go to gender, this is where we didn't get the post-hoc test, if you remember, but it's just saying, okay, male versus female, significantly different, and then it always does the reverse, female versus male, which is exactly the same. There's a difference. Okay, but what about the dose? We want to know what is the dose effect between the genders and so on, and the reverse, what's the gender effect between the doses? That's what we're really interested in. So if we come down, this is the box we want. It's the condition times gender output we want, and we want to come to this pairwise comparisons box. So this is really cool what SPSS does. If you compare male, or you look within the male gender and compare placebo versus low dose, there's a significant difference. This is the adjusted p-value box. If you look in the same gender, placebo versus high dose, there's a difference. So now we're starting to tease out the specific differences. Now this one's really good because it is a within gender comparison. We're looking within the male gender and then all the doses against each other, and then within the female gender and all the doses against each other. But it's not giving us between gender differences for each dose, but you can get that information here. So it does the exact opposite. SPSS gives you the inverse comparison. So now we can look within each dose, but between the genders, and they're all different. So this is really good. Now you start to tease out the differences between the genders, within the genders, and so on. So yeah, and it does this all by keeping the family-wise error rate at 5%. So if you run a one-way ANOVA, it's 5%. If you run a two-way ANOVA, it's still 5%, despite getting all these pairwise comparisons. So if you were to run two one-way ANOVAs, which you could do on this data, you'd go from 5% to 10%. But just running the two-way ANOVA from the start, you maintain your error rate at 5%. Anyway, that's everything. Hope you found it useful. Please subscribe, and I'll try and put out at least one video a week. All right, thanks very much. Bye-bye.